Can you all hear me?
Yeah.
All right, thanks. Give me a couple minutes and we'll get going. So my neighbor texted me yesterday and said, hey, my wife says you and I have to go out and find toilet paper. And I just burst out laughing and said, yeah, good luck with that. But I am going out to buy some stuff this morning, so I'll look. I don't hold out a lot of hope. I don't exactly understand why people are hoarding toilet paper. I mean, they're still making it same amount they always did, but every shelf is empty. I guess I'm not sure what people are going to do with all the toilet paper after this is all over. I guess they'll be set for a while. So, crisis brings out some interesting eccentricities of people. I'll tell you that. I remember one year when I just gotten here, I think, and we actually had a storm, a snowstorm, and it dumped 22 inches in one evening, which is pretty rare. And so all these people were telling me, wow, this must be just like home for you. And I said, look, crazy ass, even in Canada, 2 feet of snow is not normal. So of course the entire university shut down for a couple of weeks because they don't deal well with snow. And all the stores were closed for a few days as well. And then I noticed that the gas station up on the corner of Western, or not Western, but Avon Ferry and Gorman opened up. There's this massive line of students waiting to get in. And so I was watching it, waiting for it to open, and I was thinking, you know, they're going to get canned goods or water or something like that. Nope, every one of them came out with beer. So I forgot student priorities, having not been a student for a while. But it was probably a good choice, actually, to be honest. All right, are there any questions about anything to do with the course or whatever before I start today? Okay, so I have not heard anything back about moving assignment 4 being a problem. So I don't know for sure whether we'll get anything before the end of class, but if we don't, I will update Moodle, I will update the web page, and I will send you an email telling you what the final result of that is. All right, so we'll finish up our discussion of B-trees, and then we're going to move on to extendable hashing. Extendable hashing is the second standard method of doing on-disk based efficient searching. So the last thing I want to talk about is B+ trees. And I should mention that I didn't discuss deletion in B-star tree. Deletion is an interesting issue. So B-star trees were actually, as I mentioned, I think, invented by Don Knuth, who's the father of computer science, many of the data structures that we work on. And if you look, the only definitive discussion of B+ trees is actually in his sorting and searching fundamental algorithms of computer science textbook, reference text. And what the hell? Don't move, don't move, don't move, don't move. Thank you. And so if you look in there, he doesn't discuss deletion from a B-star tree, which would have to maintain that property of 2/3 full. And his implication is that what you should do is you should actually just use a normal B-tree deletion and accept the fact that you might not maintain the 2/3 full property, but that it'll come back again when you start inserting into the tree. And so if you wonder, well, how do we delete from a B-star tree? The general consensus is that you use a standard B-tree deletion and you don't concern yourself with the fact that the 2/3 full constraint may be violated because you're guaranteed a half full constraint. And that as long as you're using the tree for insertion deletion, most of the time you're going to have the 2/3 full constraint. Okay, so if you're wondering, what do we do with B-star trees when we delete? That's what most people do. Okay, B+ trees are actually quite a bit more popular because, as I said, they're the standard tree structure that's normally used as the B-tree indexing for database systems. Okay. So a B plus tree is a combination of a sequential in order set of keys. Sorry, a set of keys with associated offsets for the corresponding records, just like every index, together with an index structure placed on top of the sequence set. Hello, Brandon.
Are you recording?
Yes.
Sorry.
Would you like to say hello to the class?
Hello, class.
This is Brandon. Brandon runs shit around here.
Goodbye, class.
I think he was surprised to see me in here.
I was.
Do you have COVID?
No,
Okay. But still stay 6 feet away from me. I don't really like you.
that's fine.
That's cool. Yeah.
Yeah,
Okay.
we're
Thank
good.
you. All right then. Anyway, so you might wonder, what the hell does that mean? Basically what it means is that you have, in essence, a set of blocks that have the keys in order. And normally that would be a linear search, which is slow and particularly slow on disk. So what you do is you slap in a B-tree index on top of that. And so you can very rapidly find the block or blocks that you want when you're doing some sort of sequence search. So I want to find, for example, names between these two last names. And so you rapidly find the particular starting block, and the blocks are linked together in a way that makes it very efficient to pull them all out with a small set of seeks. Okay, so that's how these B plus trees work in a lot of database systems. So let's talk a little bit more about that. So the sequence set is a collection of blocks usually disk pages, because that makes the most sense in terms of optimizing the seek to data return ratio. Bound together as a doubly linked list, where an on-disk list, linked list is actually not using pointers, but it's using offsets. And the blocks form leaf nodes for a B-tree index of keys that allows rapid identification of a block holding a target key. Okay. So let me show you a quick example of that we have in the notes and the slides. So suppose we're using last names as primary keys. We would never do that, but for this example, that's what we're going to do. And in fact, in this case, you can probably, well, I think you should think of these as primary keys. So we'll just go with that for now. So just like any B tree of some order, you're going to be guaranteed some fullness. And so the B tree will be of some height, and what it'll actually have is keys, and then, as with all B trees, for a given key to the left is everything less than the key, to the right is everything greater than the key. I guess left is less than or equal to, greater than, I see. Left is less than or equal to, greater than, right is greater than. And you have things like this where you have everything from Benson up to and possibly including Cage, so on. This part up here is the index. Okay, that's just a standard B tree. Now underneath that, you have these blocks which are sized usually to disk pages. Okay, and they have key value pairs, where the key is the last name and the value is the offset into the data file that tells you where the corresponding record for, say, Adams is. So Adams is at 0, Ansell's at 200, Benson's at 2200, and then you would have a doubly linked list to another block that had, actually, let me draw this out properly, sorry. So in here is everything between Benson and Cage. So maybe we might have Bolin at 2400 and Brown at 2600. And then maybe Cage at 4800. And by the way, the fact that these are actually monotonically increasing is just completely a function of the example. In a real situation, these would be not random, but they would be all over the place because there's no guarantee that these records actually exist in order in the file. And this is doubly linked. Okay. And then down here we might have, running out of space here, but we'll put a big one in here because we're not going to have anything. So for this one, we might have I don't know, Edgar at 9600, Egan at 9800, Fisher at 11800, and again, doubly linked. And this just keeps going on until you get to the last one, which is going to have everything greater than Wyatt. So Yaz, let's say 24,000. Young at 24,200. And maybe Zarko at 26,200. Whoops. What you got, Ashton? Okay, so that's what a B plus tree looks like. So it has on the top the index and on the bottom the sequence set. And so what you can see is that if we just tried to walk through the sequence set, that would be a linear search, slow. We would be pulling in pages one after another until we actually found what we're looking for. So what we do is we actually first use a B tree index to determine for the particular key we're looking for which page has it, and then we pull that page in. So there's an extra seek to pull in the page, but we still get very nice performance. And there are some other advantages to this in terms of the fact that we can do range queries and other things like that. Okay. So are there any questions about just the basic structure of one of these B plus trees before I continue on with our discussion?
I'm still a little confused about why the pages are doubly linked.
Oh, it's actually when we do a range search, and I'll talk about this as we go along. What you'll want to do is you'll want to find usually the starting and ending, at least the starting, but often
Okay.
the starting and ending pages for the range search. And then you want to be able to very quickly walk through those without having to do any more work inside the B tree.
Got it. So instead of rewalking the index, effectively, you would walk it to find just the starting and the ending, and you would just use the fact that your leaf nodes are linked that you can walk all of them.
Exactly.
Cool.
Exactly. Yeah. That's a good question. Other questions anyone has? Okay, so let's look at how we might use this and what the pros and cons are. So here are some potential advantages. First is that the sequence set blocks are linked. So scanning a range of keys requires search for the first key and a single linear pass. Rather than multiple queries. On the B tree index. So there's lots of ways you can do this. You can look for the first key in the range, query scan, and find the block that holds it, and then just keep walking forward until you find either the last key you're looking for or something bigger than the last key, and you can stop because you know the keys are in sequential order. You could look for the last key and walk the other direction. You could find the two endpoints and walk between them. But the key is that you're not actually having to hit the B tree index every time you need a new block because they're linked. And so what you're saving here is you're saving whatever it costs to do a B tree query for the number of blocks that you're going to need to retrieve. The blocks are always going to need to be retrieved because they have the offsets into the data file that have the actual records. And so you could be saving for each block n queries, n seeks, where this n is the height of the B tree. Okay. And the second thing is that internal B tree nodes hold only keys and pointers. There's no offset values. So more keys can fit in a fixed size node, possibly reducing the height of the tree. Okay, so an offset is usually 16 bytes, give or take, 16 bytes, sorry, 4 bytes, 16 bits, maybe 8 bytes, it depends. And so you can actually fit more keys in a node if you don't have to include the offsets, because all the offsets are down in the blocks. And so more keys in a node means fewer nodes for a given set of keys, and fewer nodes for a given set of keys holds the possibility of shorter trees, which of course is going to mean fewer seeks per query. Okay. And so there's a potential that this could be a little bit faster. It all depends, right? Because you do have that extra seek for grabbing the block. And so how this is all going to pan out depends on how much data you stored in the tree and what the exact keys are. And we're actually going to talk about prefix indexes at the very end of this so that we can try to even more so squeeze down the size of the information stored in these internal nodes to maximize the amount of the number of keys that we can store in each node. Okay, now there is a disadvantage, obviously. And so if by chance the target key is in an internal node, we still need to traverse all the way to the bottom of the tree. And retrieve the corresponding block. To get the target keys offset. Right? And in a normal B tree, the offset would have been bound to the key. Okay? So in a normal B tree, you traverse down to a leaf node, and if you see your target key as you're traversing through an internal node, you can actually stop, grab the offset, and you're done. But in a B+ tree, there are no offsets in the index. And so even if you see your target key, you're still going to have to go all the way to the bottom, grab the target keys block, and get the offset out of there. So there's no shortcut, as it were, for these particular kinds of trees. But the fact of the matter is that the likelihood of seeing your target key is probably pretty small, and so this isn't going to happen too often. And so that trade-off has been accepted as not causing us a lot of problems in a B+ tree. Okay?
Is this almost like a KD tree where you need to have like a good range of values, because otherwise you could get to the bottom and you'd still have to do like a good sized linear traversal to get to the keys that you're looking for?
Yeah, I actually thought about that when I was reading about this today, so that's a good insight. It is somewhat like a KD tree in that the index above you has to be good in order for you to get good coverage for the keys. But it turns out that because of the way B trees are built, and I'll describe how it's done, it's really simple. You're automatically going to get good coverage. So you're right, you do need good coverage to get good performance, but fortunately, through the construction and maintenance of the B+ tree, you're going to get good coverage as a function of the index that sits on top of the blocks. So, yeah. Other questions, other insights? Okay, so let me just talk very quickly about how you would do insertion into a B+ tree. You'll recognize that it's very similar to a B tree with this additional block added onto the end. And then you'll see, oh, okay, so I can see why I'm going to get decent coverage. So search, insertion, and deletion into a B+ tree work identically to a B tree. But with the understanding that all operations in leaf nodes, which makes sense because there's actually no values stored with the keys in the tree, so you always traverse all the way down to the bottom. So you remember for insertion or deletion, the first thing you do is search to see where to insert or delete. So since search has to go all the way down to a blocks, so too does insertion and deletion. It's weird, like your slope on the text is a lot more than what I'm seeing. I don't know why. Could be the drugs talking. Where am I? Here we are. So as an example, to insert a key into a B+ tree, you would do the following. You would first search the B+ tree for the block to hold the key. And if space is available, because all blocks, the first block is going to start at empty because you've got an empty tree with a root node that's blank. So if space is available, and when you split, you're going to have half full blocks. You insert the key and corresponding offset value. And if the block is full, you append a new block to the end of the index file, and you keep the first k/2 keys in the existing block, and you move the remaining k/2 keys to the new block. So exactly like a B tree, you just split the overfull block into two half-full blocks. And then you update the B+ tree index using the normal B tree insertion algorithm. To link the new block into the index. So you're going to be promoting up the median key, and once you get the median key promoted up to the leaf node of the B tree index, everything happens just like it does for a normal B tree. Okay? So there really isn't any difference in terms of how a B+ tree is maintained versus a B tree, apart from the fact that you have this additional set of blocks that are down on the bottom that you have to keep managed, and they satisfy the same rules as the nodes do in terms of how they split, how they coalesce, and other things like that. Okay? So, any questions about that before I continue? Dun, 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 dun. All right, so let's finish off with prefix keys, and I think we'll probably stop at that point because the next topic is going to be extendable hashing, which is the second method of doing on-disk search. And so we will probably want to start that afresh. But I think we can get through prefix keys in not too much time, so definitely before the end of the class. So the B plus tree internal nodes hold keys that direct the search to a block that potentially holds the target key. So the key insight here is that we don't actually match the target key with the keys in the internal nodes or any of the nodes in the B tree index. We only use the target key to compare to what's in the keys in the index to determine whether to go left or right. Yes? Because we know that even if we found the target key and it matched perfectly, that offset is still not there. It's down in the block, so we're going to have to traverse all the way down the tree anyway. So what that means is that we don't need to hold necessarily the entire key value in the internal node for the B plus tree. We only need to hold enough of it so that we can do the proper directing when we're looking for a target key. And so there's an opportunity to hold less than the entire key, if less than the entire key will always give us the proper direction to go left or right when we're looking for something. Okay? So this means we only need to hold as much of the key in the internal node in the B plus tree nodes in the index to properly separate blocks, right? We just need enough information so that you know whether I should look in the left block or the right block, okay? So, as an example, recall two keys span the gap between the first and the second block. And in our example, that was Benson and Bolin. So the parent node in the B plus tree uses Benson to define that the first block holds all keys less than or equal to Benson. And Bolin is used to define that the second block holds all keys actually it's not Bolin, but it was Benson and Cage. Sorry, my bad. Because Cage was the second value in that node. Okay, so let me write this out just so it's clear. We had Benson, Cage, and then we had down here a block with everything up to Benson. And then in here, we had a block with everything up to cage. And obviously anything greater than Benson must be over here as well, right? So everything greater than Benson but less than or equal to cage is inside here. And then we have something over here, right? But if you think about it, do I really need Benson as the separator here? Because there's a lot of possible names that are greater than Benson but less than cage, right? So we don't need the entire key Benson to separate the blocks. For example, we could use BF instead. So if I replace this Benson with just the characters B and F, what you would see is that now I'm claiming everything less than or equal to BF is over here. Is that true? It is true, right? Because everything, Benson is the biggest key over here, so E comes to 4F, so anything that's BF would not be in here. So that's true. And everything between BF and cage is over here, because, and I should write in what the first value is here so that you can determine that that's true, but the first value is Bolin at 2400. So indeed, anything that starts with BF, well, BG, basically, because that's the first entry that's greater than BF, would be over here, and that's also true. So if I replace Benson with BF, I would still be directing searches correctly. You would still go to the correct block to find a target key or a potential target key based on the values that I have currently stored inside this B plus tree. And BF is shorter than Benson, so I'm actually saving 4 characters inside this internal node. All right, and if I'm saving space again, I might be able to put more keys in there. I might be able to have a larger number of splits. I might be able to have a shorter tree. So that's the entire motivation behind a prefix key. Okay. So any questions about that before I continue on and specify in particular detail how you actually build these prefix keys? All right. In general, to differentiate blocks A and B with largest key in A, KA, and smallest key in B, KB, so in our example, that would have been Benson and Bolin. Benson was the biggest key in block A, and Bolin was the smallest key in block B. It's sufficient to select any prefix key K S such that K A is less than or equal to K S is less than K B. Okay? So, for example, where we had Ka equals Benson and Kb equals Bolin, Ks equals Benson satisfies. That was how we started out, right? So Benson is less than or equal to Benson is less than Bolin. So we satisfy the equation. So Benson would be a perfectly valid Ks. But we can make it shorter, okay? But so too does the shorter BF, okay? And let me just say Ks equals BF. So if you think about it, Benson is less than or equal to BF? Yes. BF is less than Bolin? Yes. So BF would work. Okay? So if Ks has the following properties, so first Ks separates Ka and Kb, that is, it satisfies this formula. And second, no other Ks prime is shorter than Ks, then Ks satisfies the prefix property. So a prefix key is the shortest key that satisfies this property. Okay? And I'd have to think a little bit, but basically the way you do this is you take K and Kb and you start walking through them until you find a place inside them where they differ by at least 2 characters, I think, and then you just pick the character in between those 2 characters, and that will be your prefix key. Okay, so I started out and I saw BB, so those are the same, and then I saw E for Benson and O for Bolin, and they were at least 2 characters apart, so I picked something between them. I just went from E to F, and then I could say that BF is going to be my prefix key. There's no shorter key that's going to separate K and KB using that formula. Okay, so it's pretty easy to find the prefix key. Any questions about that before I finish up by explaining what that'll give us and then what we have to do in addition to what we're doing now to sort of deal with these variable length prefix keys? Okay. So by choosing the smallest Ks, we can increase the number of keys in an internal node. Potentially reducing the height of the B plus tree. And for any of these tree algorithms, we're always going after a reduction in height because that'll be a reduction in the number of seeks. Okay. But internal nodes must now manage variable length prefix keys. Okay, In the old system, we could actually define a fixed length for the key, and then we didn't have to deal with any variable length keys. But here, by their nature, prefix keys are going to be variable length, and so we're going to have to deal with that. And how do we deal with that? Well, at the very beginning of the course, we talked about within a given array or record, what are all your different choices for how you deal with variable length keys, variable length fields. And so you can use any of those. It doesn't matter which one you pick, okay? And we actually don't mind doing this because this is all going to be done in memory. And so in-memory operations are so much faster than on-disk operations. If we can save it even one seek per query, we would more than welcome the additional overhead internally to deal with these variable length prefix keys to get that free seek, okay? So simulation results suggest for trees containing between 400 to 800 pages, or blocks if you prefer. A simple prefix B+ tree requires 20 to 25% fewer seeks. Okay, so if all you do is implement this simple prefix strategy, which is very easy to do, you could improve the performance of your algorithm by 25%. That is 3 seeks instead of 4 on average, that ratio, even for something that doesn't have very much information stored in it. And that's why I said that normally we'd be more than happy to do this because the improvement is non-trivial. It's actually massive. Now, there are ways to make more efficient prefix trees, for example, by removing redundant prefix information and other things like that. But what you find is that the improvement that you get over a simple prefix tree is not very big. So unless you're really gunning for every possible percentage that you can get, you're probably not going to bother doing that, okay? The complexity is probably going to outweigh any savings that you get, so. All right, so are there any questions about prefix trees or B trees in general, or any of their variants, B star, B plus, etc.?
So if a prefix key, I guess, is expanded, you would have to expand it in such a way that you don't have to reorder how you would traverse it, right? Like, I guess that's where I'm having a hard time. So you get a sequence of keys, you come up with a prefix that properly differentiates how to traverse the tree, and then you get another key and you have to expand it. So, but you would expand that key and deal with that problem rather than trying to reorganize the key and keep the same prefix length. Is that accurate?
That is accurate. And you're also right that as we add things to the tree, it may turn out that something that was a prefix key isn't anymore. And so we're actually going to have to change the prefix key in some internal node, which could make it bigger, which could overflow that node, right? But if it overflows a node, then we deal with it in any standard method of overflowing an internal node and promoting. And so there could be more work involved than what I talked about. But it should still be fine in terms of the fact that the algorithm should continue to work as long as you've implemented the proper strategy for dealing with variable length keys inside the internal nodes of the B+ tree. Okay.
Cool.
Yeah, but that's a good point. It's not the case that a prefix key once chosen will stay that way forever. It could have to change depending on what you add to the tree. I guess when you delete, you could change them too if you wanted to, but people probably don't do that because of the fact that there's some complication involved there. All right, any other questions about any of this craziness? Good, I'm tired. Just as an ending point, and I'm already like pushing you right up to the end, even though I promised I'd let you go early. There was this idea that Saturdays would be used to actually make up the week extra that you got for spring break. And then as things sort of blew off the rails, I've never heard anything more about that, even though one of you has pointed out to me that it's actually in the academic calendar for this year. So I've asked and people are like, huh, that's a good question, but I've gotten no answer. I don't know what's going to happen, but my plan is probably that I'll come in myself on some Saturdays and record, I guess I owe you 3 lectures. And if I do that, those are going to be optional. And they'll probably be on a topic that I'm not going to include in class, but something that you might be interested in. The one that I'm thinking about is alternative storage techniques. So SSDs, magnetoresistive RAM, things like that. And so if I do that, I will do 2 things. One is I'll let you know I'm going to do it. 2 is I'll put up the Zoom invitations. They'll be on a Saturday, but I mean, if you're just sitting around doing nothing and you have no life, you can certainly watch me do it, I guess. I don't mind. And then I'll pin the lectures up for you, but they'll be optional. Optional meaning you don't have to look at them if you don't want to. Optional meaning that material would not be covered on the final exam. It's simply there as additional material for you if you have an interest in that particular topic. Okay? So I'll find out what's going on, but regardless of whether it's required, not required for me to do that, whatever, that's how it's going to be dealt with. It'll be optional. Okay? So indeed, you did get a free week where, at least in my class, there isn't going to be any more material that you need to cover on the final exam. All right, email me if you have any questions. Otherwise, enjoy the rest of your day, and I will see you on Friday. Thank you.
Thanks.
Thank you.